Assalamualaikum and a very good day. I bid to all fellow audience. First and foremost, I'd like to welcome all of you to the Advances in Geophysics webinar series, in which this special webinar is organized by Geological Society of Malaysia in collaboration with the Center of Seismic Imaging, University Technology Petronas. Now, today's webinar series is actually our 9th webinar series, and it will be mainly related to groundwater investigation. Right. So I would like to first introduce to you our honorable speaker today before passing this session today to him. So allow me to briefly share with you about the background of our speakers today. Our speaker is Dr. Stefan Henrik Gudike, who is a senior assistant professor in the Faculty of Science at University Brunei Darussalam, where he has been working since December 2016. He is responsible for teaching courses such as hydrogeology, environmental geology, introduction to petroleum engineering, and engineering geology. He has established several research projects and collaborations and supervised undergraduate and graduate students. Prior to his current position, Dr. Gudike worked as a researcher for Petronas in Malaysia, where he was responsible for evaluating the feasibility of offshore tracer technology for CO2 storage in an offshore aquifer. He has experience as a reservoir engineer in Perth, Australia, where he analyzed and reviewed geological data and mapped key parameters for a coal seam gas project in Queensland. He also worked as a hydrogeologist, numerical modeler for URS Australia Pty Limited in Perth, Australia. In this role, he constructed and calibrated numerical groundwater and solute transport models, assessed the impact of dewatering at mine sites, and calculated water balances. He was also responsible for determining suitable locations for groundwater monitoring bores and drilling rig supervision, among other tasks. Right. Now, without further ado, I'd like to invite Dr. Stefan Henrik Gudike to deliver his talk on the groundwater investigation, primarily on the fundamental and application. Please welcome, Doctor.
Thank you very much for the introduction. Thank you very much for this. It's really a great honor for me to present to you today. The title of our talk today is a groundwater investigation, fundamental and application, as you've heard. And in this talk, I would like to take you to a journey where we first introduce the importance of groundwater before we discuss some groundwater fundamentals, a few basics here. Then I would like to introduce to you the field of hydrogeophysics, and then I would like to present 3 applications from hydrogeophysics that we successfully applied in Brunei Darussalam before coming to a conclusion, a brief conclusion. Can you all hear me fine?
Yes, Doctor, we can hear you.
Okay, great. So coming to, having some discussing on the importance of groundwater. When you look at the figure here on the right, we can see this is the population over time. We can see that we have now around 8 billion people on the planet. And some of this information you can also find in the UN report on groundwater, and the population is steadily increasing. So we can really see or say that groundwater is actually an endangered resource. And from these 8 billion people, we have around 4 billion people, so like half, that are actually facing an acute water scarcity nowadays. And groundwater also accounts for 99% of all liquid freshwater. The remaining freshwater is currently tied up in glaciers and ice, but is also threatened by global warming. So because more than 97% of all the water on Earth is actually salt water. You can find different statistics where you look, but these are around the numbers. And also the Asia Pacific region is the region where we have the largest groundwater abstraction, and countries such as Bangladesh, China, Indonesia, Iran, Pakistan, and Turkey, these countries alone account for roughly 60% of the world's total groundwater withdrawal. And when you see the figure on the right is from a study by Mekun and Hoekstra from 2016. They evaluated or studied the so-called blue water scarcity. Blue water here refers to fresh surface and groundwater together. And blue water consumption is related to the volume of fresh surface water and groundwater that is withdrawn but not returned to the global water cycle that I will introduce to you a little bit later. So the figure that you see here is showing the blue water scarcity. Blue water, again, is the fresh surface and groundwater together. A blue water scarcity index, which is a ratio here between the blue water consumption divided by the blue water availability. And we see here, from this study, showed that especially regions such as Australia, Africa, the Middle East, but also here India and the US, they face the largest blue water scarcity or the water stress. And other studies, for example, the one by Ricci et al., looking at renewable groundwater stress, or like the quantifying groundwater stress, they did this study analyzing satellite imagery from the GRACE satellite that was studied in the journal Water Resource Research. They found that actually more than 21 out of 37 of the world's largest aquifers, we're going to discuss the term aquifer and also a little bit later. For these aquifers, more water is actually withdrawn than replenished. And especially if you look here on this side here, this is basically the Arabian aquifer system. This is the most distressed one. In addition to that, we have also sea level rise that is causing saline intrusions into many coastal aquifers. For example, in the case of Chennai, India, seawater intrusion from groundwater pumping has intruded into coastal aquifers several kilometers inland. And on the other hand, we can also say probably that oil, gas, and mining industries, they may have in-house data actually on location and extent of aquifers. In addition to that, we have the excessive groundwater abstraction that we mentioned in many areas has also led to subsidence in many regions throughout the world. Basically, the groundwater abstraction leads to a decrease in the pore pressure, and then that can lead to groundwater abstraction, subsidence. And our region here, the Southeast Asian region, is affected as well. For example, in particular, Jakarta, you can see here from the star that is classified like a sinking city, is a city that's affected by subsidence due to uncontrolled groundwater abstraction. But we also have uncontrolled groundwater abstraction, for example, in countries such as Pakistan, where a lot of the water doesn't even reach the customer anymore. It's even lost to pipelines, or it's like stolen by so-called the tanker mafia. And this study here from Guzi and Malinovska is based on a review, basically. Our area here with Brunei and Malaysia are not yet, as far as I know, not yet at all affected by groundwater abstraction due to subsidence or seawater intrusion. And continuing with some groundwater fundamentals now, we can say that water is really very special. I mean, it's the source of all life, as we know, but it also has the highest surface tension of all liquids. It has the highest heat of vaporization of all fluids. It has the highest melting point of all fluids. The highest density of water is at 4 degrees Celsius. That's also one of the reasons why, for example, fish can still survive in frozen climate, because this water would sink to the bottom and the water freezes from the top. And also it has a very high specific heat capacity. Only that of ammonia is higher. And looking at the effect of this, we can see, based on these facts, that vaporization will consumes a lot of energy, and condensation, on the other hand, releases energy in forms of thunderstorm, for example, tornadoes or hurricanes. And thus our oceans are really controlling the climate. The oceans can also absorb a lot of heat energy from the sun. And this is, we already mentioned the hydrological cycle. This is basically what the hydrological cycle or the water cycle we can also see as an energy cycle, with the main energy coming from the sun. And we see here groundwater as a key part of the hydrological cycle. And as we can see, is as expected, the groundwater would flow towards the ocean, and like the field, for example, of submarine groundwater discharge, the groundwater that flows into the ocean may have an effect on the nutrient balance in the ocean, is also an area that is field of active research. Then we have, of course, the infiltration, and if the infiltration capacity of the soil is exceeded, we get overland flow. We have evaporation and transpiration over land, but clearly most of the evaporation is occurring over the oceans. And then we have, of course, precipitation, condensation, and rivers here, as well as glaciers. Many people may think that, okay, most of the available fresh water is in rivers, but this is actually only a very small, tiny percentage compared to groundwater. We already mentioned the term aquifer. Now maybe it's time for us to get a definition of it. What do we actually understand as an aquifer, as key part for like groundwater investigation, or if we want to investigate groundwater. So aquifer is really, it can be a solid rock or sedimentary layer that has voids or pore space and has a certain permeability as well. On the other hand, now we can ask ourselves, okay, that's true, but all rocks have voids and all rocks are somehow permeable. So we should say that actually an aquifer is basically is a system that has a large void volume or porosity and a great or a good permeability, or we call it hydraulic conductivity in groundwater hydrogeology. In particular, also the sedimentary aquifers are actually the ones that are more important compared to solid rock aquifers, unless the solid rock aquifer on the rock aquifer or fresh rock aquifer or the rock aquifer is highly fractured or highly weathered. These aquifers, they can interact with each other, and they form distinct hydraulic units. What you see here on the picture on the right, we have different important types of aquifers shown here. The confined aquifer is the one here that I'm pointing out now. This is a unit that is bounded by a confining unit, which is often a clay or shale at the top and the base. And the water level, if a well would be drilled into this confined aquifer, the water level in a confined aquifer would always be above the or inside the confining unit. It would not be inside the confining aquifer itself. It would always be above or even further up. If it reaches the surface, then it would be a flowing artesian well. This is a special case of a well that is drilled inside a confined aquifer, or in this case here is artesian well. We see here the groundwater, the water level, which is marked always as a upside down triangle to mark the water level surface. Basically, this is the zone where we have 100% water saturation, and above that we have the so-called unsaturated zone, where we have a three-phase system, and we have water, air, and basically solid material all together as three phases. And then opposing to the confined aquifer, we can distinguish an unconfined aquifer. An unconfined aquifer is the one that has a free water table. This is what you see here, has a free water table. And if we dewater an unconfined aquifer, we are actually really dewatering the pore space. Whereas for a confined aquifer, during pumping also the water and the aquifer would still remain fully saturated. And for a confined aquifer, actually, if we need to pump the same amount of volume compared to an unconfined aquifer, we need to usually induce much more head drop in order to pump the same amount of volume compared to the unconfined aquifer. You can also distinguish a so-called perch aquifer that we see here on the top. These are often not very regional extensive. They can, for example, be aligned with clay units or shale that can lead to these aquifers to be close to the land surface. And then we have also here marked recharge areas. That's where the water, like in, for example, hill zones, where water preferentially infiltrates and reaches the fully saturated zone or the groundwater zone. After learning some basics here on different types of aquifers, we can also remember that aquifers can actually be very extensive. They can be, for example, they don't stop at the border between Brunei and Malaysia. They can cross borders, and if they do, which is common, they would be called transboundary aquifers. And this is also a field of increasing research probably over the last 15-20 years, especially when it comes to water management. I'll introduce to you now one of the key basic laws that we use when it comes to groundwater. And this is the law by Darcy. Darcy was a French engineer who lived between 1803 and 1858. And he actually found this law when he was investigating or doing experiments on water circulation in glass tubes that were filled with sand and used for water treatment at that time. And he found that the change in water level, or we call it hydraulic head, between, let's say, 2 points here, you see H1, H2, along a flow distance L, is actually related to the so-called permeability or hydraulic conductivity of the sand. And what I'm showing you is just here the very basic one-dimensional law, Darcy's law. So which here is the V is basically the so-called Darcy velocity. Then we have K as a hydraulic conductivity of the sand. This is a property of the fluid as well as the material. which is the sand or whatever we are flowing through, whatever geological material is we're having here, as well as the hydraulic, so-called hydraulic gradient, which is defined as a change in hydraulic head over the change in length over which the flow occurs. This so-called, this hydraulic conductivity has the properties of velocity. So, but this Darcy velocity is not a real true flow velocity. If you want to know the real true flow velocity of the aquifer, we would have to divide this by the effective porosity to really account for the groundwater velocity. Permeability is often used synonymous with hydraulic conductivity, but it's not exactly the same. The permeability has the units of an area. Then we can ask ourselves for groundwater investigation, how can we actually get access to groundwater? How can we measure like depth to groundwater? Because that's probably one of the first things we want to do. So there's natural sources, for example, springs, where we could get access to groundwater. But we can also have artificial groundwater exposures. For example, it can be deep excavations from construction, or we can have from tunnels and mining. A lot of the mining, for example, from pit mining, the groundwater investigation becomes very important from the point on where these operations go below the water table. Then we have drillings, well, and groundwater measuring points, and hopefully we can agree that later on the talk that hydrogeophysics or geophysical methods can really help us to reduce drilling, because geophysical methods can actually better help us to pinpoint on certain drilling locations. Let's say if we have a well or groundwater monitoring point installed, how do we measure the depth to groundwater in this case? There are several methods. One is a classic method, is so-called electrical contact gauge. And a very popular one is also the pressure sensor. We have this load with automatic recording is probably not so popular anymore. And then the ancient one is a well whistle, but maybe it will get a revival because there's a cheap method to measure depth to groundwater. This is basically a hollow pipe that is lowered into the well. When it reaches the water surface, the displaced air will travel through this hollow pipe, and if the opening of this pipe is shaped the right way, a whistling sound can be emitted. So this groundwater, this electrical contact gauge, as you see here, we can lower it into the well, and this is our basically sensor here, shown in the silver color. This sensor, once it reaches the water surface, it is basically lowered on a tape that has an accurate length inscription on it. Once it reaches the water surface, an electrical circuit is closed when it comes in contact with water, and a light or a sound can be emitted. Then we have very popular nowadays pressure sensors. They can be also lowered into the well, like the electrical contact gauge, but whereas previously we just had to do manual work, manual readings, these actually can be programmed and can store or record data over longer time periods in intervals that we choose, for example, 1 minute, 1 second, every 5 minutes, and it's powered by a lithium battery generally. And this data can be stored in the data logger itself, in the memory, and then can be downloaded via software. And from the pressure, we can then also record actually we can get information on the depth to water on the water level. Usually they have to be compensated for atmospheric pressure, because the atmospheric pressure also can influence the groundwater elevation, especially when the groundwater level is close to the surface. When the groundwater level is close to the surface, we can also have evaporation occurring from the groundwater as well. So if we have now 3 groundwater measuring points or groundwater monitoring points, what can we do with those? And we know that those points are actually not on, we also know those points are not on one line. And those points, and let's say we have this electrical contact gauge, or we have a pressure sensor, and we know the height, let's say, we know the topographic height as well as the upper edge of the pipe that we installed it, because usually we have a stick-up height above the ground surface that we need to account for. If you know all this, then we can actually determine the direction of groundwater flow. And this is an important aspect for groundwater investigation. So let's say we have these 3 points. From a groundwater monitoring point, we know actually now the exact height of the groundwater level. Then we can determine the direction of groundwater flow from these 3 measurements by linear interpolation. What I'm basically showing you here. We're connecting this. It's now obviously can be done by hand, but nowadays this can be done nicely also through software. And we have now established basically lines of equal groundwater elevation, and the flow direction is this blue line that is situated at a 90-degree angle on this groundwater equipotential, or lines of equal groundwater elevation. And in this case, it's 90 degrees because we are assuming here that our hydraulic conductivity or permeability is homogeneous in all directions, and we only have one permeability or hydraulic conductivity. But in reality, we may have it may be much more heterogeneous, and also we can say here that the hydraulic conductivity or permeability is actually directional dependent as well. But for a simple case, we can assume it like this. It's also very good if we do groundwater investigations, any kind of investigation, to try to understand about the type of aquifer that could be present, and in what kind of depositional environment this aquifer was actually deposited, or how did it form. And I'm just showing you here one case for the formation of an aquifer. Could be formed from fluvial sediments, but for example, it could also be aquifers. We could also have aquifers in volcanic sediments, glacial sediments, or arid deltas, basin formations. But from formation of fluvial sediments is also a common one. I'm showing you here, it could be generated from a river that is over geological time. It meanders, moves, and incises into the bedrock, and as it does this, this river could meander over time, and could form these so-called oxbow lakes, where they were formerly part of the river, but then were cut off at some point. And then we can have typically sediments such as clay and silt that are more associated with the floodplain deposits for silt and clay, as well as sand and gravel that are more associated with the bed load deposits that would be deposited more where higher flow velocities at the river were present. And we could even distinguish, and we do further analysis on the possible flow direction of this river, or even on the shape of the gravel, potentially how far this they have been traveled from their point of origin. Coming now to the field of hydrogeophysics, we can really say that there have been several geophysical tools that have been used in hydrological or hydrogeological investigation already for decades. For example, well logging tool or the gamma ray tool. And hydrogeophysics started to emerge as a separate discipline only in the late 1990s. And here the focus has been, and why did it emerge like this? Because the focus became more on an improved understanding of hydrogeological processes using geophysical techniques on the shallow subsurface, because the shallow subsurface is really critical for us humans here, just thinking about agriculture, environmental pollution, and so this is how it started to emerge. In my talk, I won't be actually going through a lot of the, fundamentals or equations here, because I would not be able to give justice to everything in this time frame. But for example, if one wants to go deeper, you are welcome to look, for example, literature, just as one from Bindley, Electrical Methods for Fundamentals, or there's a book on hydrogeophysics by Rubin and Hubbard. And the picture that you see here on the right is actually a depiction of this hydrogeological heterogeneity that we could face, and which could be common, like a more complex scenario where we have actually sand, gravel, clay, and bedrock that are all deposited and from different have different thicknesses and different locations, and we have our groundwater zone here, as well as the possible river. And then we see here, in this case, electrical conductivity, this colored figure, that can be that we derive or that we get from our geophysical measurements. And this electrical conductivity that can then be potentially related to hydrogeological properties. One key challenge is that our geophysical measurements actually, they do not provide the direct information about the hydrogeological properties. So we cannot, from our geophysical measurements, we cannot directly get information about the permeability. We cannot directly get, okay, what is the exact porosity? But we can get information on that I'm going to show later, that is very useful for us to know more about the lithology, for example. And we need to translate the raw geophysical measurements to a pattern of geophysical parameters. And this is usually achieved in a so-called inversion process. So what we see here on the right, this case for wellbore geophysics. So we're taking a series of measurements, and this data is basically gridded, and then through inversion function, we can derive the spatial pattern of our geophysical property for basically one snapshot in time. What we see here in this colored figure on the very right. And also the interpretation of those results that we get, it can be challenging, because it's the so-called non-uniqueness problem, meaning that we can have theoretically more than one solution. So more than one distribution, for example, of the parameter could be possible. The electrical methods are the most widely used, we can say the most widely used near surface geophysical methods for environmental application. And why is that so? Because the theoretical concepts of the analysis and also the the conduction of the surveys is relatively straightforward, and also because the subsurface electrical properties, they can usually be quite well correlated to physical and chemical properties of fluids in the pore space. And these fluid properties could be, for example, saturation or salinity. And it is commonly done, these electrical methods commonly done using so-called electrode arrays that are placed at the surface using different spacings. And common ones are like the Wenner array that you see here on the top right, in the middle the Schlumberger array or the dipole-dipole array. And we have here the I depicted as the electrodes where the current is injected, and V is the electrodes where the differential of the electrode, the voltage is measured. So we already mentioned the electrical methods, or sometimes it's called the direct current resistivity. These are, as I mentioned already, conducted using electrode arrays on the surface. And we usually calculate, or what we usually get from this direct current resistivity measurement, we get like a apparent resistivity. It is the only other formula I'm showing you guys, apart from the Darcy's law. This is the formula for the apparent resistivity. It's basically, it would be equal to our geometrical factor, and which depends on the electrode spacing, and I is our injected current, and dV is the voltage difference between the electrodes. Then our measured apparent resistivity, or as we later see, we can also look at chargeability values. Again, they do not really provide directly a model of the subsurface geoelectrical properties, so we have to do use modeling tools and apply so-called we use inverse models to determine the geoelectrical structure for a given set of measurements. Once we have this geoelectrical structure, in this case, what you see here on the right again, the electrical conductivity, we can then try to relate this to properties such as water saturation. And as I already mentioned this, those are the electrical methods are most widely used. And what you see here on the figure on the right, this is this is one of shows actually our electrical resistivity measurement device that we have in our faculty here. So we have the main unit, we have our electrodes, we have the cables for the current, as well as for the injection of the current. And why it's also so widely used, because why hydrogeophysics is also so popular is because the measurements can be highly scalable from just tens of centimeters to hundreds of meters, and the instrumentation is comparatively low cost, and also our analysis methods and modeling tools are already readily available and robust for the analysis. What you see here on this figure is a comparison for the three different electrode arrays that I introduced to you guys earlier. For example, distinguished here between depth of investigation, vertical resolution, for example, signal strength, and we can see here that for depth of investigation, for example, the pole-dipole method is good compared to Schlumberger and Wenner method. pole-dipole is similar to the dipole-dipole that you see on the right bottom, but for the pole-dipole, that one current electrode is moved far away, more than 10 times the distance of the survey area. And then we have, for example, for vertical resolution, the Wender method is preferential over the other two, or for vertical sounding, the Schlumberger method is highly applicable. This is one I will show you from the case study from Brunei in a little bit, where we used vertical electrical sounding using Schlumberger method. And then we can then look at different types of the geophysical methods. This table we're not going to go through in all the details, but we can see here the geophysical properties we measure, and then some examples of derived properties such as water content or clay content or pore water conductivity that we can derive from it, if possibly. Often the direct current resistivity method is done together with the so-called induced polarization method. And in this case, the so-called chargeability or apparent chargeability is measured, and this chargeability from the induced polarization that actually relies on the effect that the current, when it's after injection, when it's switched off, it doesn't straight away go to zero, but it tapers off with time. So, and then this dropping off of the injected current is then measured, and then this measurement can require longer measurement times sometimes than the direct current resistivity itself. Also popular is the seismic method. I'm going to show you in one case study where we use seismic refraction to try to differentiate between different lithologies and as well demark the groundwater table. Some newer methods here, you can only pointing out is like nuclear magnetic resonance. I also don't have don't have experience in this part. I'm just showing here for completeness. We're already coming now to some case studies from Brunei, and this is one of the case study from my former PhD student, Sitiliana Asri, and in this case, we investigated a rice farming area. And the background for this is that actually Brunei wants to become more self-sufficient with regards to rice, to grow rice throughout the growing season. And since not in many areas, not enough water is available all the year round. So we looked at different study site here, and we focus here in this case on one where that is actually close to the Malaysian border here. We see the Limbang River on the right, and usually the water comes from the Imang Reservoir for irrigation, but often when it comes to the paddy field, it may not be sufficient enough for the farmer anymore. So this was also a government initiative to investigate if groundwater can be used as potential irrigation method. That's also where we came in a bit later to do our study. And but we not only investigated just groundwater, we also looked at the soil. So for groundwater investigation, we used the vertical electrical sounding method using Schlumberger array. And the soil investigation that we see is shown this round dots. That's where we did soil investigation close to a well that was drilled, not by us, or was drilled prior, but unfortunately it was unsuccessful because it was completed in a clay zone, because we have very thick clay unit here due to floodplain deposit, but the well was still pumped for a while in a form of a pumping test. Usually once groundwater is found and the well has been drilled successfully and completed, usually one thing is being done, a pumping test or well test is being performed. So this was also done for this well. to try to find out how much water can be pumped from an aquifer. From the vertical electrical sounding, I should show you one example. We were able to see different hydrogeological units here. We could differentiate between the topsoil, that is also PT in our area, and then we had a very thick, often sometimes more than 60 meters, or up to 60 meters in this case, clay zone. And then from our investigation, we could see that there potentially below that there is a possibility of an aquifer, but we would actually have to do more. We would have to do more investigation and also possibly some drilling to really, if we want to focus in on a drilling location for a pumping well. From the soil investigation that we've done, this is a result from the soil investigation we had shown here on these figures. You always see plot 1, 2, 3. This is basically related to, if I may go back here, these are to these plots here, 1, 2, 3, that you see on this right figure. And maybe just remember that plot 1 is the one that is closest to the pumping well. And for this case, for the plot that closest to the pumping well, we saw that pH actually, and also the water saturation, but also nutrients were distinguishably different. So from that, we confirmed that actually we interpreted it that way, that groundwater pumping actually had influenced these, also basically the soil in the area. So it's always good, or it's highly important once, for example, groundwater abstraction starts, to keep monitoring not only water levels with time, but also soil or water quality as well. This is another study that we've done in collaboration with University Technology Petronas from a student, Adli Azar, and together with Dr. Abdul Halim from University Technology Petronas. And we looked here at the Baracas Forest Reserve, which is actually close to our university, where we applied seismic refraction along different survey sites. And we were able to, and very quite nice data was obtained. But what we see here for one survey site, we see here the shot points 1 to 7. They're basically shot points where we strike with a sledgehammer onto the metal plate to create the energy for our geophones. It's basically the geophone setup is shown here on the right. We measured along a survey line, and the raw data, just for completeness, probably is a bit hard to see, is shown here as well. And we can see what we usually get is what distinguishes is so-called travel time distance curves. And we use this data then to distinguish between different layers or horizons. And we were able to determine up to 3 different layers. And the good thing about it also was that we were able to distinguish the water table. It was what we see here from the P wave velocity that is measured. In this case, it was always around up to around 1,500 meters per second. So this blue zone is where we interpreted the groundwater level to be, and above it the unsaturated zone, or the weathered zone. And then we could use this data from different survey sites to get to understand, okay, where is the groundwater table, but also where could the flow, where's the flow going to be, and what are the hydraulic gradients. And we could correlate it also with springs at different locations in the area. In this case, as expected, the flow was towards the South China Sea. We also did some geochemical investigation of the groundwater and found that it's actually quite acidic due to acid sulfide soils in the area. And this, from the success we had there, we were quite, we were like a bit confident after this study, and we applied the seismic reflection study at another site, this time more challenging environment in a peat swamp area in Badas. The Badas peat dome is one of the largest peat domes is the largest peat dome in Brunei Darussalam. That what you see here, shown in dark green. But it was cut in half basically once because a water pipeline was built or road was built to connect it to the Tutong River. What you see here at the right bottom of the picture. And this is a study from my former master student, together with also researcher from Institute of Biodiversity Environmental Research from UBD and the Singapore MIT Alliance of Research and Technology, Dr. Alex Korb. And several survey sites were done. And here the focus was more on, or was also on looking at the degradation of the peat and what effect human activities may have on the peatland. This is just, so as I mentioned, it's more challenging for this to the geophysical investigation here, because on the left picture, this is like a degraded peatland. It can be very challenging to move around, and on the right is like a more pristine peat swamp forest. This because normally the peat land is always forested. But still we are getting some also very good data from our seismic study. We could correlate it with the cores that were drilled here up to 5 meters. And the deep blue is again where we have fully saturated peat. And above it, we have the unsaturated peat. Oh, sorry, the blue zone is actually the saturated zone. In this case, it's actually clay and low moisture clay. And above it is peat. But what the seismic reflection method could not distinguish here was a top sand layer. But it correlated well with the coring. For example, you see here the other small, very thin layer, right? It's slightly different from the bottom blue one. That's basically what relates to our low moisture clay layer. So we're already coming at this point to the conclusion of our talk, and we can really say that groundwater is an endangered resource. Hydrogeophysics is a useful tool, definitely has been a useful tool for us here for hydrogeological mapping, but also possible monitoring of hydrogeological processes, maybe flow direction or hydrological parameter estimation. Electroresistivity imaging is the most widely used geophysical method for environmental shallow surface applications. But we should not forget that the result can be difficult to interpret because of the non-uniqueness of the solution. But definitely geophysical applications with regards to groundwater investigation, they will continue to emerge and will be promising tools for us to provide insight into really the really pressing environmental problems that we all face, and especially also with regards to groundwater management. With that, I really thank you for your attention, and thank you again for inviting me. I appreciate it.
Right. Thank you, Dr. Stein, for the very insightful sharing on the understanding of the fundamental and application of the groundwater investigation. Right, so now we will continue with the Q&A session. So for the audience, if you have any question that you'd like to ask Dr. Stefan, you may do so by turning on your mic or typing your question in the chat box. Mr. Robin, do you have any question?
Nurul, thank you.
Yeah.
Maybe I just start the ball rolling. I'm in a way surprised to hear 99% of the groundwater is actually fresh water. It's not the river, it's not the lake. It's actually the groundwater, it's 99%. That is something new to me. So thank you, Dr. Stephen, highlighting that.
Thank you.
Also, where I'm living now, I'm living in Perth. You've been to Perth also.
Okay.
The problem that I see, is not much of land subsidence or seawater intrusion because of the groundwater withdrawal, but the withdrawal from the wetland. The water table of the wetland
Yes.
goes down. So that affected migratory birds. The migratory birds fly from Alaska, from Siberia, 13,000 kilometers. So they come here during the summer. So to feed, to do nesting. And when they come, Forest Day Lake, for example, there's no water. So because the water has been drawn down by groundwater withdrawal. So that is the problem. I saw your case study in Brunei. You were studying this groundwater in a paddy field, in a swamp pit. Is there any problem with land subsidence?
That's a good question. Thank you for your explanation, for your comment and your question.
And also seawater intrusion. Are there any problem with because it's near to the sea?
Yeah, we currently we don't have yet any problem with seawater intrusion because we don't have yet any larger pumping well situated near the coastline, but that may come in the future. For example, when a groundwater well is drilled, for example, for fish farming, for example, to supply water or something like this, or for industry. But currently there's no issue with seawater intrusion, but we have definitely issue probably with the drainage from wetlands, because the peatland is a concern that water drains from the peatland, and then if this water drains out, we have subsidence issue that could lead to increased flooding. Definitely, for example, we can saw at the one site that I showed, we had where the pipeline was constructed, their subsidence was already, at least we can see from the piling that was done to install those pipes, that at least subsidence was already over 1 meter, 1.50 meter probably there at the site.
Okay.
But it's something that should probably needs more attention, research.
Also on your geophysical method, the normal method would be resistivity to determine this water table, because water is conductive, so it will show very well in the image. But I'm also surprised you also use seismic. How? That's interesting, because seismic is based on bulk density. So you're measuring in meter per second. How you detect these aquifers with that method?
Okay.
It's interesting.
In this case, we use the seismic reflection method, and that we correlated the p wave velocity through and we correlated this to also with the literature, and then based on also correlated with springs as well, and then we could in this case pinpoint the water tables or saturated zone from seismic reflection quite confidently.
Probably because
and usually the p wave velocity in this case was like around maybe 1,400 to 1,500 meter per second for the fully saturated zone.
They would travel faster in the saturated zone.
Yes, yes.
Yeah, I see. Okay. Thank you.
I see we have other questions here also in the chat box.
Yes.
Thank you for the question.
Thank you, Mr. Robin. Then we have also another two questions from the chat box. So the first question is from Mr. Adam Hashim. He was asking, dear doctor, do you think the aquifer near the paddy field is some kind of riverbank filtration? Thank you.
That's a good question. Like I mean, it is. I mean, riverbank filtration is more like a application, but this could be is done in, I believe, is successfully done in other countries, but it could be a potential way of also of deriving suitable or getting a suitable water from an aquifer. So in riverbank filtration is basically where we install a well close to a river in the saturated zone, and then from pumping we also basically draw the river water through the porous media zone, and is a way of filtering this river water. But it's more like an application, but it could be an interesting way to try to get more water, like I mean, as a water source, alternative water source, because currently Brunei is only relying mainly on surface water for drinking water purposes, not yet on groundwater. I believe Malaysia is different in this regard, right? So riverbank filtration is really like an application where you install a well close to river, and then you start pumping and you draw the river water through the aquifer that is present, and then filter it a little bit that way. But one still need to confirm whether the sediments there are non-clay. Basically, it should be completed not in the clay or in the silty zone. Should be in the sand or a gravel, ideally. That's a good question. We have another question here on the the groundwater's pH drop? Why would the groundwater pH drop or become more acidic nearby the well? This could be something that could be related to if the groundwater level drops, then the sediments could be, if in certain areas, become more aerobic, or because if it's fully water settled, it would be anaerobic, no oxygen. If it becomes aerobic, then it could lead to some geochemical reaction, for example, some sulfide oxidation that could lead to a pH drop. So possibly related to some geochemical reaction that are leading to the water becoming more acidic nearby the well due to the drop in water level from after pumping that well.
Okay, thank you, Doctor. And listening for the question. I think Robin has another question. Robin?
Yes, Dr. Stephen. Following Mr. Tang question regarding this pH water drop, you mentioned about the water drop because of the water drop. Possibly there's an oxidation of sulfide take place. Will the pH, just a question, will the pH return to normal if the water the water table is been raised? Just wondering. Raised to its normal level when you stop pumping.
Yeah,
or
that's
it will,
yeah.
or it will remain as 5 because it's already been that particular field has been there's so much sulfide there already. Just wondering.
That's a good question. I mean, there's something probably one has to do more monitoring, or like more long-term monitoring. But for example, we found in another study but this maybe this in this case for surface water reservoir that we studied here in Brunei, where after the surface water reservoir was raised, the water level was raised in order to account for more, because we can't get more drinking water for the population, increasing population. And after the raise in water level of the reservoir, all of a sudden pH started to increase by over 1 pH unit.
Increase, become acidic.
The pH become more.
Increase, alkaline.
Yeah, more alkaline, and that was like a puzzling for us. It's but even after 2-3 years, the pH has actually not gone back yet. So and we think it's due to the oxidation of, the reduction of ferrous iron oxides in this case. So also again geochemical reaction that coupled with bacteria that use organic matter in the process that could lead to these geochemistry changes.
Yeah, that is good then, because acid mine drainage, we mine and then expose this sulfide ore in the mine pit, and then the whole system become acidic. But as you mentioned, if you can fill up the pit with water, then that will solve the acid mine drainage problem.
Okay.
Just fill up the pit, it become a lake. It wouldn't be as acidic as it should be.
Yeah, like peatland restoration, like revetting, that's definitely something that is of importance here.
Okay.
Do you have any other question? from the audience?
Sorry if you hear my
Sorry,
if you hear my cat meowing in the background, sorry then. It's my cat.
Okay. Mr. Ravi, do you have another question? Because I could see.
Not for me.
Oh, okay.
By the way, Dr. Sipan, if you're still there,
Yes.
what would be your favorite resistivity configuration? The dapur scale major or the Werner?
I think this depends on the what I mean on the type of what we would like to investigate. I think I think for shallow investigation, for example, peatland or so, I would probably maybe use Werner.
Yeah, simpler. Yeah. Have you used the dapur before?
I haven't used it yet. I just interpreted the data though. I mean, but I haven't used it yet myself.
Yeah, it's for deeper investigation. Yeah,
We're currently looking also into I mean, doing ERT study, like doing resistivity tomography or resistivity imaging with a multi-electrode cable.
yeah.
Right. Thank you again, Mr. Robin, for the question. So, so before we end, is there any other questions from the audience? We still have some time. Or is there anything that you, Dr. Stefan, would like to maybe add or something?
I think I'm okay. I mean, I want to say thank you again for inviting me, and I wish you all a great afternoon.
Well, thank you, Dr. Sipan, for your great presentation and explanation of the geophysics of groundwater. And
Thank you so much.
Yeah, a lot more. Thank you.
Thank you.
And about this, the groundwater distribution, and also can use a seismic to study groundwater imaging. Yeah, and also to rectify acid soil. Just cover up with water. It will help to mitigate the problem. So thank you, Doctor.
Okay. So since there is no more question, I think that will be the end of our session today. So I would like to thank again Dr. Stefan for becoming our honorable speaker today. I believe that all of us have gained so much new and valuable insight and inputs from your sharing just now. And so just before we end our session today, just a kind reminder for all of the audience, please kindly fill in the attendance Google form link for this webinar, which I have shared with all of you in the chat box. You can find the link in the chat box. And so I hope to see all of you again soon. Thank you so much for your participation today. And with that, assalamualaikum and goodbye, everyone. Thank you again, Dr. Stefan, and thank you, everyone.
Also,
Thank you very much.
Nurul,
Yes.
thank you for letting me know how to rectify my name.
Yeah, sure.
All right.
Okay. All right. Thank you.
Thank you very much. Thank you.